Okay, let's go over some problems about roots and fractional exponents. So in these problems, we're going to simplify so that each variable appears at most once and there are no fractional powers. So the first one is square root of x squared divided by y to the fourth. This might look pretty simple, but it is actually a little more complicated than you might think. So one thing you could do, there's multiple ways to do this, but one thing you could do is you can break up or distribute a root over the top and bottom of a fraction. So I can break this into square root of x squared over square root of y to the fourth. And now you might be saying, okay, square root of x squared, that's x. No, it is not x. So what is the square root of x squared? It's absolute value of x. And I'll convince you of why that is in a second. And now, confusingly, for the bottom one, I'm just going to do y squared. You could do absolute value of y squared, but you don't have to, because by squaring, that's already going to make whatever you put in there positive. So you don't need to do that. Now, sidebar, y is square root of x squared, absolute value of x, and not just x. The reason is because when you plug in things like -3, the first thing that happens is it gets squared. So then you're taking the square root of +9, and that's 3. So you don't get back in what you plugged in at the beginning. You get back the positive version of whatever you plugged in at the beginning. Same thing if you plug in a positive number, it comes out positive. Okay, so whatever you plug into square root of x squared, you get back the positive version of that x. So that's why this is absolute value of x. Okay, it is also, it's also absolute value of y squared. It's just that happens to be the same thing as regular old y squared. So don't have to write it like that. So this is something that you have to worry about whenever you have an even power. And it's particularly annoying in the context of fractional exponents, because with fractional exponents, I'll just do another like sidebar or side cloud. When you have something like, let's say y to the 2/4, you might think that you should just go ahead and cancel this and make it y to the 1/2, but that actually would not necessarily be the same thing. Because if your y to the 2/4 started out like this, fourth root of y squared, then that's an expression where no matter what you plug in for y, even if it was negative, it would come out positive. So this should actually be interpreted as absolute value of y to the 1/2. If you just wrote it as y to the 1/2, then it would be, that's the same as the square root of y, but you can't plug in negative numbers to the square root. But back here, you could plug in negative numbers, right? So this can't be the same thing. If I was able to put in negative numbers before, and it's equal, then I should still be able to plug them in. But it's actually this, absolute value of y to the 1/2. So this is just a really kind of annoying thing that happens whenever you have an even power inside an even root, or to say it the same way, you have a factor of 2 in the top and bottom of a fractional exponent. It's the same thing. Something you frequently have to worry about. Now let's look at one where we do not have an even root. So if there's no even roots, then you don't got to worry about this at all. So let's do one like that. So we're doing cube root of a cubed b, and that's all being squared, and then b to the 4th. Okay. So what I'm going to do in this is I'm going to distribute well, there's a few ways you could do it. So you could distribute or break up the cube root over these two factors, like put it around this one and then put it around this one. That's one way. Or you could write it as a fractional power and then do the same thing. So I think I'll do it like that. Write it as a fractional power. And then I'll distribute it to these two factors. This is one factor. This is another factor. They come with their powers on. So this is a cubed b squared, and then that's being raised to the 1/3. And then I have b to the 4th, and that's being raised to the 1/3. So I'm going to multiply this 2 power times this 1/3 power, and this 4 power times this 1/3 power. So now I'm going to have a cubed b, and then 2 times 1/3 is 2/3. Okay, and then I have b, so 4 times 1/3 is 4/3. And now I have two factors here. I have the a cubed factor and the b factor, and I'm going to distribute the 2/3 to both of those. So I have a cubed to the 2/3, and then I have b to the 2/3, and then I have b to the 4/3. Okay. So once again, I'm going to multiply the 3 power here times the 2/3 power here, and I'm going to write it as 6/3 for now because I'm feeling a little bit nervous about canceling factors in fractional exponents. And here I have b to the 2/3, b to the 4/3, so I can add these two powers together. 2/3 plus 4/3 is 6/3. Okay, so I have the same fractional power on each of a and b. And now I'm thinking like, oh, does this have something to do with absolute value? So fortunately, we don't need to worry about absolute value here. It's when you have a common factor of 2 in your top and your bottom of your fractional power, that's when you have to worry about absolute value, because that's when you've got an even power inside of an even root, which always makes, no matter what you plug in, it always makes it come out positive. Okay, but here we're going to cancel a factor of 3, and that's going to leave us with just 2 for the power. So 6/3 is 2. So a squared, b squared. As it happens, these would come out positive no matter what you plugged in. That's just a coincidence. Okay, so let's do one more. And I'm not sure if we need to worry about absolute value stuff in this one or not, but let's find out together. So this is cube root of z squared divided by square root of z cubed. Oh, someone is messing with us. It was me. I wrote this problem. So the top one, I'm going to interpret this as z squared to the 1/3, or you could just go ahead and write it as z to the 2/3. And on the bottom, this is z cubed to the 1/2, or z to the 3/2. So now I'm multiplying the 2 and the 1/3 power together, so I'm getting 2/3. And on the bottom, I'm getting 3/2. Okay, so now I have something to a power over that same thing to another power. I can subtract the powers, so top power minus bottom power. So this is z to the 2/3 minus 3/2. You might notice we always write fractions that are in exponents like kind of sideways or diagonal. It's because if I write it upright, then it might get too big and I might think it's being multiplied by z instead of being the power. Anyway, so now I'm just going to do like a little sidebar over here, side cloud. What is 2/3 minus 3/2 anyway? Guess we got to get a common denominator. So I'm going to multiply the fraction on the left by the other one's denominator over itself, and the fraction on the right with the other one's denominator over itself. So they'll both end up with a denominator of 6. Top times top, bottom times bottom, 2 times 2, 4. 2 times 3, 6. Still have a minus. 3 times 3, 9. 2 times 3, 6. Now, if you have 4 apples and you take away 9 apples, I think you have a debt of 5 apples, so minus 5 apples. Apples and sixths work the same way. So 4 sixths minus 9 sixths is negative 5 sixths. And that is going to be our new power on z. So coming out of the side bubble here, we have z to the negative 5 sixths. And I believe up here we were told to simplify so each variable appears at most once. So I've done that. And I want no fractional powers. So how do I write this no longer as a fractional power? I guess the negative power is okay. Nobody told me not to do that. But I could also, if I wanted to, write this as 1 over z to the positive 5, 6. And then what this means is this is z to the 5th, and it's the 6th root of that. So let me erase this mistake here. It's z to the 5th, and then we're taking the 6th root of it, like that. I suppose since it wasn't in the instructions, we could have also left it as z to the negative 5th, and then take the 6th root of that instead of moving it to the denominator. Either way seems fine. I've been forgetting to box my answers, but let me box that one. Final answers. All right, that's it.